So we already had a little sneak peek last time, and we saw an example where we solved an interpolation problem of 3 points, right? We set up that matrix. So based on that, now we're going to look at the general situation. So I will have a data set. So this is my data. I have a set of data containing all these points, xi, yi. I runs from 0, 1, and 2, n. So n plus 1 data points, and I want to interpolate it. So the goal is to find a polynomial of degree n such that Pn interpolates it. So Pm at xi exactly equals to yi for all the points, right? So we can write out this polynomial. Let's just write it because we're going to work at it today. So I'm going to write this in the order of increasing power, okay? Not as we did last time. So it's the same thing. So I'm going to start with a constant term, a0, a1, x to the power 1, a2, x squared, and then I increase to all the way to an xn. Is that okay? So I have n plus 1 unknowns. So very often in numeric computation, these are also called degrees of freedom, meaning how many things are unknown you could adjust to fit in what you want to do. Okay, so these are also as degree of freedom. So n plus 1 degree of freedom. No, that's so bad. So you know what I mean, degree of freedom. Okay, and then there are exactly n plus 1 constraints. So if they match, there shall be a unique solution if well posed. Okay, so what I want to do now is to set up these n plus 1 equations and just take a look at them. Okay, so this part shall be okay. So I have n plus 1 constraints, so let's put it in. Pn at x0 shall be y0, right? Each of these give me equation. So what I will do will be, I will write out the first equation, the second equation, and then you see it's obvious how it's going on. And then we put dot, 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 and we write the last equation. Okay, so we cannot write so many. Okay, so when x equals to x0, this polynomial returns the value y0. So write it out. So this will be a0 plus a1 x0 plus a2 x0 squared plus an x0 to the power n equals to y0. Is that okay? Okay, so do the next one. If you put in x1, you get y1, right? So we did this computation last class, but with 3 points, with values. Now I put in symbols. Okay, so this is a0 plus a1 that I change into x1 now. An x1 to the power n equals to y1. Yeah. Is it okay to read from the back of the class? It's clear? Okay. All right, and then you see the pattern. I just change it into xi, and then it should equal to yi. So let's go to the last equation. When it's xn, this shall equal to yn, right? So let's set it up. So this will be a0 plus a1 xn plus a2 xn squared plus all the way to an xn to the power n equals to yn. Okay, so n plus 1 equations and n plus 1 unknowns. Look at each equation. What are your unknowns? Keep your heads very clear. What am I trying to solve here? The a's, right? And all these x, they are data, they are given, they are numbers, I already know. All right? Keep that clear. Okay, so these are your unknowns. So what are my unknowns? Are these a's. So a0, a1, all the way to an. Okay, so are each of these equations a linear equation with respect to the unknown? They are, isn't it? That they all are, because x is just number, right? Okay, so you have a system of linear equations. Okay, so you go to MATLAB, you say, help me out, can I solve it? Can you help me solve it? So as we saw last time, we should write it into matrix vector form, right? Then it's easy, that's what MATLAB is designed for. So let's do this. If I want to write it into matrix vector form, we did it last time. Okay, so I will have a n plus 1 times n plus 1 matrix, and then I will have an unknown vector. What is my unknown vector? Are these a's, so a0, a1, dot, 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 an. And I have a load vector on the right-hand side. That will be my y0, y1, and yn. Is that right? So what do I do with the coefficient matrix? How should I fill it up? So now you see why I put the a0 term first. If I prepare it like this, all you need to fill in is the coefficient in front of unknown in its corresponding place right there. Fill it in the matrix. Is that right? So the first column will be what's in front of a0, right? So it will be 1 and 1 and 1. Is that clear? The second column will be what's in front of a1. That will be all these x, x0, x1, all the way to xm. And then the third one will be, no, I'm sorry, 0. That always bites me. It starts from 0. Starts from 0. Okay, so the next one is x0 square, x1 square, all the way to xn square. Is that right? And the power increases as you go further down into more columns. And then the last one will be to the power n. So is it clear how to set this up? Right? Okay, so let's write it as a notation. Let's call this matrix capital X. This big X. Usually capital letters are for matrix. Okay, and this is my unknown vector. It's a vector, column vector A. Let me put an arrow to say that's a vector, right? And then I have the right-hand side, which is Y with the arrow. It's the vector. So you have basically AX equals to B, so it's XA equal to Y, the same thing. You can give it to MATLAB to solve. Okay, so let's talk a little about this matrix here. This capital matrix X, it's a n plus 1 times n plus 1 matrix. Okay, so it's a special matrix designed for this purpose of polynomial interpolation, and you see that what's in this matrix here are only these data points of X, right? Once this set of X is given, you know x0, x1, all the way to xn, then you know this matrix X. Nothing else is needed, right? So this one carries the name. It's called the Vandermonde Matrix. I mean, it doesn't take that much effort to generate this matrix, but to make life even easier, it's already coded in MATLAB. Okay, so you just need to launch this command. So that's the prompt in the command window. In MATLAB, the command will be Vande. They don't care about the monde, the whole word doesn't matter. They just pick the Vande. And then what you send in is a vector containing all these x's. Is that clear? So let's say you were putting x0, x1, let's put a comma, x2, depending on how you set up the vector. Or you can send in an x. Bless you. You can send in a little x as long as you know it's a vector. You give it in, it will generate this matrix for you. Question?
Is the bracket necessary Like you got two brackets.
If these are numbers you type in, 0, 1, 2, 3, then you have to do this bracket. Yeah. Okay? But if x is already a vector, then you just put x in. It takes a vector.
Right.
Is that clear? Or I could write it like this, Vandermonde x, where this x you should already have defined. It's a vector. Let's say 1, 2, 3, 4, whatever, how you defined it.
Okay.
All right? Okay, either way. So, very sweet, there's not much you need to do. Then you can call the inverse of capital X. If you let's be specific. Let's say you say capital X equal to Vande, and then that's a matrix you have there. And then you can solve it by inverse X times Y, right? Okay, so that's very, very good news, but always there's a catch. Bad news. This is the first method we introduced for polynomial interpolation. That can't be the best, right? That's the most obvious one. It's obvious, so you can do it, but there's some bad news here. So the bad news lies in the following sense. That is, now I have a matrix times a vector equal to something. I want to solve this system of linear equations. So, when you give this y to the computer makes an approximation, right? So there's some round-off error already in when it stores it. And then you ask the computer to solve it. What the computer gets is an approximation. Is that right? And there's a little bit error in the y. So you will be wondering, this little bit error in y, how big a difference will it cause in my actual solution? Okay. So this is called stability with respect to perturbation. You perturb a little bit data, how does the outcome change? Is it very sensitive that it changes wildly a lot, or it changes also very small? Okay, so if it's unstable, then any little perturbation will throw the solution off. Okay, so one thing we haven't learned that yet, later on we'll touch up, all that lies in some properties in this coefficient matrix. Okay, so there is one quantity called the condition number of the matrix that determines. So if you have a very big condition number, that's bad news. The condition number, the smallest condition number it can get is 1, which represents an identity matrix. Then there's nothing to do. Okay, but all other condition numbers will be bigger than 1. The bigger, the worse. So the bad news for the Vandermonde matrix is, for n large, it doesn't really have to be very large. Say you can put in n equals to 10. You can go to MATLAB, give x 1, 2, 3, 4 all the way to 10. Okay, ask MATLAB to generate this matrix X for you, and then you ask MATLAB to compute the condition number. The command is COND, and you give this big X the matrix in, you see a huge number. What does it mean? That means the solution is extremely sensitive to perturbation, and that's very bad. Okay? Very bad. Okay, so bad news. So very large condition number. So what does it mean? It's very sensitive, unstable. Okay.
What's a condition number?
It's the largest eigenvalue divided by the smallest eigenvalue in absolute value. We'll get to that. Yeah. So identity matrix has all eigenvalues equal to 1. Condition number is 1. That's the best. Yeah. Okay. So we'll look at some other ways of doing it. So one way we would do now, bless you, Lagrange polynomials, interpolation polynomials. So Lagrange is a French mathematician. His name appears at many places. Okay, so this is a very, very elegant construction. Okay, I explained this to you. I hope you can appreciate how nice it is. Okay, so the same problem, give the data set, I want to interpolate it by polynomials. So this starts with the data set of x, x0, x1, dot, 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 to xn. You give me n plus 1 point, and I will construct something called, we define some function called the cardinal functions. Okay, that's what I'm trying to define here. And these are called L. L actually stands for the Lagrange, Li. Okay, so let me write it, L0, L1, Ln. There will be n plus 1 such cardinal functions, each one associated with each point that you're representing. So Li will be associated with xi, okay? So these are polynomials of degree n, okay? Satisfy the following. So if you look at the ith cardinal function evaluated at the grid point xj, okay? Can one see this is I, this is j? It's okay? So that equals to the Kronecker delta. Okay, I'll explain. Maybe you've heard of the delta. Have we heard of this delta function? We have, maybe not all of us. So what does it mean? It carries two index I and j. When I equals to j, it returns the value 1. And then if I does not equal to j, otherwise, it gives me 0. Is that clear? So this holds for all the points, 0, 1 to n. Okay. So what does it mean? Well, this basically says if I only care about the discrete points, then the cardinal function is very locally supported. Do we know the support of a function? And you know, we say a function is locally supported, meaning the function is non-zero on the interval where it's supported, right? The support of the function is where the function is non-zero. So if I only care about these discrete points, then each cardinal function is supported only at one point. And at all the other discrete points, it takes value 0. Okay, so it's a local support property. So, okay. Locally, very locally supported, discrete sense, okay? Discrete sense. Yeah. Okay, so now what I will do next will be I will write out exactly what these cardinal functions will be, because we know they are polynomials of degree n, and we know exactly what they will be. Okay, so Li of x, the ith cardinal function associated with xi takes the following form. It's a product for j from 0 to n, and j does not equal to I. Okay, so how many terms will I have here? If you just run from 0 to n, there are n plus 1 terms. And then I take away 1 term. So there are n terms being multiplied, right? Each term is a linear polynomial. It gives me a polynomial of degree n. Okay, so each term takes the following form. X minus xj over xi minus xj. And then you let j run from 0 to n. And you see clearly, if j equals to I, it doesn't make sense. So j cannot be I, right? Is that okay? So let me write it out into the product form. So how would it look like? Let's say I is some intermediate index, not the first or the second, otherwise I have to stop right away. So this will be a big fractional expression, and on the top I will have x minus x0, x minus x1, all the way to x minus xi minus 1, right? Then I don't take the term xi. I skip one term here. I move to I plus 1. Is that right? Do you see? Index skipped one. xi is not here. Okay? And then all the way to the last one. Is that okay? And the denominator copies the numerator and turn all the x into xi. And that's all. All right? So it will be xi minus x0, xi minus x1, xi minus xi minus 1, xi minus xi plus 1, xi minus xn. So in the denominator, these are all numbers. So the polynomial is on the numerator. Is that clear? So I say this will do the job. Let's verify. Does it do the job? It needs to satisfy that property that it's a Kronecker delta. So Li, let's say if I put it in xi, does it equal to 1? I want it to be 1, right? What do you think? If I put in xi, what do I have? xi minus xj over xi minus xj. Each term is 1. I multiply 1 n times. What do I get? 1. That's okay. Is it clear? What about the other part? Let's say x, let's use a k. Should I use a k? Okay, where I does not equal to k. What do I get? I want to show this is 0. So is it 0? Now you have xk here, right? For some k, and k does not equal to I, and your j run from 0 to n, and does not go through I, there will be one value of j will exactly match the k, isn't it? And that term is 0. And then it kills everything, right? If you multiply by 0, you're 0. Is it okay? Is it clear? So 0, okay. Now we have the cardinal functions. So why do we bother making these cardinal functions? Well, that's actually the hard work. Once you have them, you have the polynomials. Let's write out. I can set up Lagrange form of the interpolation polynomial. It's the following. So Pn of x will equal to summation I from 0 to n. I'll just take the cardinal function that I have there, and then I multiply with y, I. So take each cardinal function and multiply the cardinal function with the value, the data, y there, and then add them all up. Do you believe this function interpolates? It's clearly a polynomial of degree n, right? Because each cardinal function is a polynomial of degree n. So we need to verify. So we need to verify that it interpolates. What do we need to verify? That is Pn, if I put in xk, it shall give me yk. Is that right? For all k from 0 to n plus 1 point. Does it do that? So let's see. What is Pn at xk? So I from 0 to n, Li at xk times yi. Every time you see this expression, you should be very happy because you know most likely it's 0, it can only be non-zero when these two numbers match. Is that right? It's all 0 except one term when I exactly matches k. It's 1, right? And then I one matches k, so it's y, k. Do we see? Is everyone with me? That's all. So it interpolates the data. Very nice, right? Are we okay? So let me block what's important. So this is important, the property of the cardinal function. It's okay, that's a nice formula. And then the expression for the cardinal function. All right? Yeah, question?
Does the Lagrange polynomial give non-zero values for x's that aren't in the data? So Pn of x that is not included in your vector will give a non-zero.
It can't, right? It's a polynomial of degree n. You mean the cardinal function or the Lagrange?
The Lagrange polynomial.
Can it be 0?
Is it non-zero for anything that isn't included in the data?
That's not relevant here, right? You mean, is it for any value of x, this thing can be 0? Yeah, it's a polynomial of degree n. It can have most n roots.
For any value of x, is it defined?
Yeah.
Is it non-zero?
It's defined for all x. It's a polynomial. We are interpolating our data sets. We don't care the 0 about this polynomial. Yeah, but the cardinal functions, they are defined in that way. They are polynomial. See, the cardinal functions, this is polynomial of degree n, and then I already know that there are n zeros. It will not have any other zeros. That you can say. Agree? Yeah. Okay, so I want to emphasize that also. Okay, so those 3 formulas, we get them. Okay, so, all right, so we find another way of solving this problem. Let's slow down a bit and take an example. Just to get our hands on it. So example 2. So what I will do will be, I will take the same data as we had in example 1 we did last time, and then we'll try to use the new method. Okay, so 0, 1, 2 over 3, 0.5, and 1, 0. That's the data. I could not help sort it out the x. Is it okay? It doesn't matter if I sort it or not. It looks nicer that it's increasing. Okay, it doesn't matter. Okay, so we want to find the Lagrange polynomial for this one. Okay, so let's try to see how we can do it. So let's write the x0, 0, x1 is 2 over 3, x2 is 1. So you know the hard work is to figure out these cardinal functions. So let's do that. L0 of x, what would that be? Well, we have the 3 values for my x, so all I need to do is just throw in this formula and work it out, right? So when index is 0, I will skip the first term. So x minus x0, I will not have. I will have x minus x1, x minus x2, those 2 terms, right? And what's in the denominator? Well, that's exactly the same as numerator, and I change the x to x0, the same index. Okay, so this will be x0 minus x1, x0 minus x2. Is that clear? I just want you to actually see one cardinal function. Okay, so let's put in the numbers. So this will be x minus 2 over 3, x minus 1, and down here is 0 minus 2 over 3, 0 minus 1, right? So you see it's a polynomial of degree 2. I could probably work out the denominator. It will be 2 over 3. I flip it. It's 3 over 2. X minus 2 over 3. X minus 1. Is that okay? Would you be able to do L1 and L2? Would that be okay? L1. Okay. So what should I put in? Should I take the term x minus x0? Yes. I will skip the term with x1, right? This term will not be here, but the 0 will be here. So it's x minus x0, x minus x2. I skip the x1, right? And then the denominator is the same as the numerator, where I change x to x1, right? So if you see, the pattern is not that bad. Okay, so you put in the value of x1, x2, x0, and evaluate. Let me give you the answer. Is that okay? That's what you will get. I did not simplify, only lumped the denominator and worked it out. So the last one. Okay, let's do the last one. So how would it look like? So it will be x minus x0, x minus x1. But don't take x minus x2, right? So what's the denominator? Anybody wants to tell me what would be the denominator?
x2 minus x0.
Change the x into x2, right? x2 minus x1. Okay, so if I work it out, I would not give you the pleasure of watching me work it out. I just give you the answer. That's the mental part. Once you know the correct formula, you can just fill in and get it, right? Okay, so actually I'm not that smart. You will discover very soon. I was being silly. So what is the polynomial? P2 of x. I know from the last formula we have there, this would be y0 times L0 of x plus y1 times L1 of x plus y2 times L2 of x. Is that right? So I would always write this step, okay, in the exam or whatever, just to show whoever is grading that you know this formula before you plug in the value, okay? There's no rush. You can always plug in the value. That's the brain part. Plugging, that's the arm part. Okay, so let's plug it in. Y0 is 1, so this guy is multiplied by 1. Y1 is 0.5, and it's multiplied here, so actually I get negative 9 over 4 x minus 1. And then I have one more term, y2 times L2. Well, what's y2? It's 0, so there's nothing to add, isn't it? So I actually didn't have to work this out, did I? It's not needed, L2. It will be multiplied by a 0. Okay, so we used another method to find the interpolating polynomial for the same data set. Now, if you're curious, you shall be thinking, is this the same polynomial as the one we get by using the Vandermonde matrix? Do you think I get the same polynomial, or is this a different polynomial? What do you say? Well, the easiest way to do is just go ahead and verify it, right? Can I expand this and collect like terms and write it into a polynomial with powers of x? If you do that, you open up and you collect like terms, and this is what you get. Negative 3 over 4 x squared minus 1 over 4 x plus 1. That's what I get if I didn't mess up. Is it the same as what we got last time? Yeah, it's the same, isn't it? Same as in example 1. So with two different methods, we actually found the same polynomial. So you shall be thinking, does it always exist just one and only solution? Is it solution unique? Okay, we'll come back to that. All right, so any questions on this Lagrange form? Is it clear how it's been done? Okay, let's be the critic and look at this and try to say something good about it and try to criticize it, okay? Pros and cons. Okay, anything good about this method? What do you feel like? I think those that are geeky, fond of math, I hope you would agree with me if I say it's very elegant, isn't it? Do we agree? It's rather elegant, and you have to agree that. Do you have to? Elegant. Because, I mean, you can just write it out and that's it, right? Basically, there's no other more computations to do. Okay, so these are from the math favored group, people will say that. Okay, then we are also computer scientists because I have to code this in MATLAB, and the computer will have to do all the work and compute and give me the polynomial. In the end, I want these three coefficients, don't I? Do you think it's a very efficient method? Is it very quick to compute? I don't think it's that quick, isn't it? Each cardinal function takes so much fuss to get, right? And each one is different. You computed L0, and you cannot use it for L1. You have to start all from scratch, and everything is different. So I have to say heavy to compute, slow. Okay, so that's one drawback. And now, if this is offered as an algorithm, I would usually want some flexibility. Flexibility in the following sense. So you're interpolating some data with polynomial or some function with polynomial. So your hope is if I insert more points, my polynomial shall be more accurate. Some way you were thinking like that, right? Or you do a data experiment, and later after you interpolate it, you did another experiment, you got additional data, and you want to interpolate that as well. So I want some method that can allow me this flexibility by adding extra points, but not having to redo the computation all over again, but I could save what I already have and just modify on that. That's flexibility, right? Does it offer such flexibility? No, we're so critical. Not flexible. What does it mean with respect to adding more points, right? If you just add 1 point, you have to do it all over. Not nice. Okay. Anything more you wish to say about the Lagrange?
If you would add on more points to get a more accurate polynomial.
Not really. We'll come to that. Yeah. Yes and no. Okay, depends on how you add it. Okay. Yeah.
Isn't the Vandermonde matrix also not very flexible?
Exactly. If you have more points, you can do it. Yeah. So here comes the next one. This is a topic that has been so much studied. Okay, so now we want to look at another method that the main aim is to allow flexibility. Okay, so I don't think I'll finish that today, but let's just get started and we'll continue next time. So when you see this name, you know the lion has been here. This is due to Newton. Divided differences, okay, the name will explain later why it's called that, okay? So the same problem, you want to find polynomials that interpolates the data, but the main idea is the following. I want this flexibility. So I want to design some algorithm. It's kind of iterative. So let me write it down. So if now I have a polynomial pk of x, I already know that it interpolates, let's say, k plus 1 points, right? The first k plus 1 points in my data. Okay. Can I keep it and use it to find the next one, pk plus 1, which would interpolate the same data, the k plus 1, the same k plus 1 points, plus 1 more point. Is that clear, the setting? I wish to define this function, this polynomial, including that one in it, and just make modifications. Okay? So I don't throw away all the hard work that I have already done. Okay. So, we'll start a few steps today. So, okay, so it's iterative. So let's go from the smallest number, n equals to 0. I want to find a polynomial that interpolates one data. The polynomial shall be degree 0. Is that right? What will it be?
0.
We set p0 of x shall equal to y0. It's a constant. Is that right? Okay. All right. 2. Add 1 point for n equals to 1. And then I have to find a polynomial of degree 1. So my polynomial of degree 1, p1 of x, will be constructed in this way. I'll keep the p0, and then I add an additional piece. Okay? I don't throw away. So the additional piece is in this particular form. a1 is a coefficient to be determined. I have x minus x0. So what's the advantages of having this thing here? So you know, for any AI, without even notifying, without even finding out what these AIs are, I already would know that A1s, I already know that P1 would interpolate the data point x0, y0. Do we see? So let's check. I already know that P1 at x0 will equal to y0. Do we see it? I have P0, y0, plus, what do I add on top? Isn't it? Right? This term is 0 when x equal to x0. And then this polynomial interpolates, x0. So that's just y0, because that's the constant function, right? So, okay, so we have another condition. Now we must check. The second one is that P1 x1 must equal to y1, right? An additional condition. So what does that give me? So this is P0 at x1 plus a1 x1 minus x0 shall equal to y1. We can use this to find this a1. Do we see? Everything else we know. We can find a1. Okay, you just manipulate. So this guy is y0. I could move it to the right-hand side, and then I can move this under. So I get y1 minus y0 over x1 minus x0. That's my a1. We okay? One more step. Still far away from getting it. Okay, let's add one more point. So n equals to 2. Now I want the point x2, y2 also to be interpolated. So we will set the next polynomial in this form. P3 of x will be built on top of P2, the one we just found there, plus I add something else. So this will be x minus x0 What do you think I will put up? Anybody reads my mind? What will it be? What will I add here? Yes. Why is this a good choice?
So I'm a little confused with the notation. So this is for n equals 2. So is it p sub 2x equals p sub 1x plus a sub 2? Or is it...
N equals 2 means I do 3 points.
3 points?
Yeah.
Okay,
So your data is like this. Your data set is x0, y0, x1, y1, x2, y2. Each step I go, I first interpolate, and then I pick up one more point, and then I pick up one more point. Right now, when n equals to 2, I will be interpolating 3 points.
So should I be P2 of x
Yeah.
equals P1 of x plus A2?
Yeah, I jumped an index. I'm sorry. That will be the next one, right? Next one, yeah. Okay, so do you agree that with this construction, this holds? Do we see that? How about this holds also for free? Do we see? Okay, then we need to check the last condition, that P2 at x2 must equal to y2. Is that right? Give me 1 minute, I'm done here. Okay, so let's put that in. Then I have P1 at x2 plus A2 at x2 minus x0, x2 minus x1 shall equal to y2. Is that right? Everything's given. A2 is the only unknown, so I can write out A2 would be y2 minus p1 of x2 over x2 minus x0, x2 minus x1. That A2 will do the job. Is that right? Okay, so we'll stop here, because right now, looking at the expression for A2 and the expression for A1, I don't see really a pattern. We'll have to manipulate the expression to get the iterative property, which we'll cover next time. Okay?